polynomial functions and complex zeros, or if you prefer, complex roots. All right, so we went through a whole lot to do with rational roots and real roots. Now we're going to talk about non-real roots or complex roots, complex zeros. In particular, our objective, use the Conjugate Pairs Theorem, which we'll define toward the end of the lesson, to find remaining complex roots. Okay, what do we know that's going to be applicable for this video lecture? We know that the set of complex numbers includes the real numbers. Okay, so now normally when we talk about complex, we're only talking about those that are imaginary, but we need to remember that the complex number set includes the real numbers. For example, we can write the number 5 as 5 plus 0i. Okay, so here is its complex look, if you will. Okay, we also learned in a previous video lecture what a conjugate is. Okay, conjugate, the same two terms with the opposite sign between them. And we saw conjugates in two situations. The first situation involved imaginary numbers. The conjugate of 3 plus 2i is 3 minus 2i. Again, the same two terms with the opposite sign between them. And we also used conjugates when we were talking about rationalizing denominators with square roots. Okay, so the conjugate of 4 minus the square root of 5 is 4 plus the square root of 5. Again, same two terms. In this case, they're both numbers, opposite signs. All right, we also did some work previously with quadratics, so let's take a look at that. When we solved quadratics, the solution set could be two non-real numbers. So here's a quadratic, okay, x squared plus x plus 1 equals 0. We remember that to solve a quadratic, set it equal to 0. I'm going to go straight to the quadratic formula because I know these are non-real roots. So x is equal to opposite b is 1, plus or minus the square root of b squared, 1 squared, minus 4 times a is 1, times c is 1. All of that, the entire piece of that, divided by 2 times a. Okay, this is equal to negative 1 plus or minus. This is 1 minus 4. So this is negative 1 plus or minus the square root of negative 3 over 2. Okay, well that's equal to negative 1 plus or minus I root 3 over 2. Remember, the square root of negative 1 is I, so we can factor the I out. And if we wrote this in complex form, negative 1/2 plus or minus root 3 over 2i, those are your two roots. They're both complex roots. Negative 1/2 plus root 3 over 2i and negative 1/2 minus root 3 over 2i. So we did that back with our quadratics. Okay, let's take a look at some things as we begin to look at how complex roots work with our polynomials. Okay, so let's find the zeros of these functions. And let's also write each function in factored form. Now let's take a look here quickly. A, the highest degree of x is a 1, so this is a linear function. Degree 1, this is a quadratic, also a degree 2 function. I got 2 degrees here. When I multiply, this is 1 degree, so I wind up with a 3rd degree polynomial or 3rd degree polynomial function here. Okay, so let's find the zeros. Let's set this equal to 0 in letter A. Subtract 4 from both sides. and the 0 here is negative 2. And let's also write the function in factored form. Okay, f of x is equal to 2 times x plus 2, and there's where you can see your negative 2 comes from right there. This quadratic, okay, you solve these by setting them equal to 0. Let's subtract 9 from both sides, so x squared equals negative 9. And we come up with, well, the square root of negative 9 is positive or negative 3i. In factored form, f of x is equal to x minus 3i times x plus 3i. That's factored form. And now let's look at this quadratic. Now we already did this, okay? We already did x squared plus x plus 1. And we came up with these two factors right here. Okay, I'm going to jot those down on a piece of paper so that I can see them. Okay, so those are our two factors right here. Going to go over to here. So I don't need to, of course I set this equal to 0. Okay, so 0 equals x minus 1 times x squared plus 1, x plus 1. And then we solve it. Well, we know x equals 1 here for this factor. And we've already factored this quadratic. And it told us that x is equal to negative 1/2 plus or minus root 3 over 2 times I. Okay, so in factored form, f of x is equal to x minus 1. I'm going to factor this as this. So x minus, I'll put a parenthesis in here, negative 1/2 plus root 3 over 2i. And I hope I can make it fit. X minus parentheses, negative 1/2 minus root 3 over 2i. Barely fits. Okay, but you can see I have three factors. X minus 1, x minus this one, negative 1/2 plus root 3 over 2i, and x minus negative 1/2 minus root 3 over 2 times I. Three factors. So let's notice a few things here. Let's jot down some things we see looking at these three examples. One is a degree 1 polynomial, linear. B is a degree 2 polynomial, also called quadratic. And a C is a degree 3 polynomial. So we're going to notice, number 1, the number of roots, the number of zeros, equals the degree of the function when we include complex roots. Okay, now of course they're all complex. Even this is a complex, but in this case, complex means the imaginary numbers. Okay, we include complex. First degree, 1 root. Second degree, 2 roots. Third degree, 3 roots. Okay, 1 is real and 2 are non-real in this case. And these two are both non-real roots, and this is a real root. Okay, number 2. Let's also notice the number of linear factors equals the degree of the function when we include complex roots. Okay, take a look. Here's a linear factor. Here, this is degree 1, linear, and I have 1 factor. Number of factors, and of course, notice all these factors are linear. There's no exponent above these factors. They're all linear. Okay, so degree 1, 1 linear factor. Degree 2, 2 linear factors. Degree 3, 3 linear factors. And finally, let's also notice, okay, if a complex number, and again, I'm using the word complex here as it has an I. Okay, if a complex number is a root or a zero, okay, its conjugate, okay, its conjugate is also a root. Okay, so look here. If 3i is a root, negative 3i is a root. Okay, if negative 1/2 plus root 3 over 2i is a root, its conjugate, negative 1/2 minus root 3 over 2i is a root. Okay, so those are three things we notice we're gonna make use of. Okay, we want to know those things and we're gonna make use of them. Well, this points us to a couple things we want to jot down. The first of those is the fundamental theorem of algebra. So the fundamental theorem of algebra. For those of you heading on to calculus, you will learn about the fundamental theorem of calculus in your Calculus 1 study. Okay, this says every polynomial f of x of degree n greater than 1, so we want to have at least a linear function, has at least one complex zero. Okay, now remember, R-E-M-E-M, okay, remember the set of complex numbers includes the real numbers okay. All right. In fact, so that's the fundamental theorem of algebra. Every polynomial function of degree 1 or greater has at least one complex zero. Again, if we go back up here, you can see this function, linear, has one complex zero. This has 2. This has 3. Every one has at least one. That's the fundamental theorem of algebra. But in fact, and this is the part we want to focus on, so I'll put a big star next to that. In fact, every polynomial function of degree n greater than or equal to 1 can be factored into n linear factors. Okay, so the degree matches the number of linear factors. Okay, however, but put a caveat to this, they are not necessarily distinct. Okay, we want to remember multiplicity. So you might have one factor that appears twice. That counts as 2, even though it's the same factor. If it counts twice, because it has a multiplicity of 2, it counts as 2. Okay? And thus, every polynomial function, every polynomial function of degree n has exactly n complex roots. Now don't forget, remember, complex roots includes the real numbers, okay? Some of which may repeat. Okay, so this is the part right here. I'll circle that piece right here. Okay, every polynomial function of degree n has exactly n complex roots. Now again, complex includes the real numbers. Okay, but you might have some that repeat. So you might have some multiplicity going on, but you can count. If it's a degree 5 polynomial, you have 5 roots. Okay, you might have 1 real and 4 complex. You might have 3 real, 2 of those reals repeat, multiplicity of 2, and 2 complex. But every polynomial function of a degree has the same number of complex roots. Okay, let's make a chart that kind of puts this together a little bit. I think that'll kind of help you take a look at how this works, at least to a degree 4, which is most of what we're going to work with. So I'm going to do a degree in this column. And I go down 1, 2, 3, 4, I think. I'll go down to 5 for etc. I'm going to do roots in this column. And then I'm going to do possible combination. And the rest of the paper here. So the possible combination can get pretty big. Okay, so we have a degree 1. A degree 1 polynomial has 1 root, because again, every polynomial of degree n has n roots. In this case, the only possible combination is its real, 1 real root. You're not going to have 1 complex root. We'll see why in just a moment. Degree 2, a quadratic. A degree 2 has 2 roots. Okay, you're either going to have 2 real roots, or you're going to have 2 complex roots. Now remember, we saw in quadratics that the quadratic may just touch the x-axis, in which case your 2 real roots are both the same. Again, you could have a multiplicity of 2 here. So your 2 real roots will be the same root. Okay, a degree 3 polynomial has 3 roots. Your combination, you could have 3 real roots, or you could have 1 real and 2 complex roots. Those are your possible combinations. You can either have 3 real or 1 real and 2 complex. A degree 4 polynomial will have 4 roots. Your combinations, you could have 4 real, or you could have 2 real and 2 complex, or you could have 4 complex. Those are the possible combinations for a degree 4 polynomial. And again, if they're all 4 real, you could have some multiplicity going on. So you could have your roots could be 1, 1, 1, and 3, for example. But as you list them out as linear factors, you'll have 4 real roots. But don't forget, you could have duplicates, and the 4 counts duplicates as individuals. Continue with your degree, etc. Possible combinations. We won't go any further with this chart. Okay, so now let's put this, let's do a couple of examples here, and then we'll come up with the Conjugate Pairs Theorem. Okay, example 1. How many zeros, how many roots does the polynomial f of x equals 3x to the 5th plus 2x cubed minus 4x plus 1/2. Well, the answer is it's degree 5, therefore it has 5 zeros. Degree equals 5, so 5 zeros. Okay, 5 zeros. Okay, so let's take, out of curiosity, let's take a look at this graph here. So I'm going to slide this up a touch, and I'm going to graph this 5th degree polynomial. I got to clear out what I had in there. So 3x to the 5th plus 2x to the 3rd minus 4x plus 1. I'll zoom to my standard just to start myself off. And there it is. Okay, so it looks like I'm gonna zoom in a touch to take a look closer at around the origin. It looks like it just takes off and goes up and takes off and goes down on the ends. So let's zoom in a little bit. Let's go from -4 to 4 on the x-axis, and let's see the area around the origin. Okay, so this looks like we have 1, 2, 3 real roots, or real zeros, which means we're going to have 2 that are complex when we do the math. So, okay, the graph shows I think my paper's straight. The graph shows 3 real roots and 2 complex roots. Again, real roots cross the x-axis. Those are x-intercepts. Complex roots are out there somewhere. They are solutions, but they're not going to cross the x-axis because they're imaginary. Okay? So, let's talk about the Conjugate Pairs Theorem. Okay, now let's go back briefly and let's take a look at a work on the previous page. We'll come back to here. When we were looking at these zeros of these 3 functions, notice that our imaginary roots come in pairs. Okay, they come in pairs. We got positive negative 3i, negative 1/2 plus or minus root 3 over 2i. So our complex, we wrote down here, if a complex number is a root, its conjugate is also a root. So we noticed that before. The Conjugate Pairs Theorem puts that down as a theorem, okay? Puts that down officially. And what it says is, if, you've been using colons, I'll put a colon there. If a plus bi is a 0 or a root, right, okay, of the polynomial function, so of f of x, then a minus bi is also a 0 of f of x. So this is nice to know. Conjugate pairs theorem. Your complex roots come in pairs. Okay? So we can, if we know one, we know a second one. We know the other one. Okay? If we know one complex root, we know the second complex root because it's the conjugate of that. So let's put that into example, and that'll wrap up this video lecture for us. Example 2. Okay, a polynomial of degree 5, okay, has zeros of 1, 5i, and 1 plus I. Okay, find the remaining zeros. Okay, well, what do we know? We know it's a degree 5. We have 5 zeros. And we know that every complex imaginary root has its conjugate is also a root. So they should be listed. So we know, hey, wait a second, 5i. We know if we have 3 given, we have 2 more to find. Well, wait a second. If 5i is a 0, its conjugate negative 5i is also a 0, because conjugate roots come in pairs right up here. Okay? Similarly, with 1 plus I, if 1 plus I is a 0, its conjugate, 1 minus I, the sign between changes, is also a 0. So what are the 5 roots? So the 5 zeros or roots for this 5th degree polynomial are 1. Okay, the complex numbers come in pairs, so 5i and negative 5i. Those are 3. 1 plus I and 1 minus I. Now we have all 5 roots. Doing no math, thanks to the Conjugate Pairs Theorem. Okay, we're now going to get into polynomials and solving polynomials with complex roots and finding polynomials whose zeros are given, coming right up.